Recall, the basis of the proportional distribution is the binomial distribution. Let's briefly review the parameters of the binomial distribution. N is the number of trials, P is the probability of success for one trial, Q is the probability of failure for one trial and is always equal to 1 minus P. X is the number of successes in N trials. P of X is the probability of getting X successes in N trials. Using this equation, we can calculate the probability of X successes in N trials. The mean of a binomial distribution is given by this equation and is N, the number of trials, times P, the probability of success for one trial. The standard deviation of the binomial distribution is given by this equation and is the square root of the product of N, P, and Q. Remember, Q is the probability of failure. So for our example binomial distribution, N equals 5 and P equals 0.5, therefore the mean of the binomial distribution is 2.5. The standard deviation of the binomial distribution is the square root of 5 times 0.5 times 0.5, therefore the standard deviation of the binomial distribution is 1.1180. If necessary, review the video on the binomial distribution. The proportional distribution is nothing more than a binomial distribution. The interest now is in the proportion of successes in N trials and not the number of successes in N trials. To do this, we divide the values of the horizontal axis by N. So for this example, instead of going from 0 to 5, 5 being the value of N, it will go from 0 to 1. This can be thought of as going from 0% to 100%. We must also divide the equation for the mean by N. Doing so, we get P as the mean of the proportional distribution. Dividing the standard deviation equation by N, we get the square root of P times Q divided by N. Using the parameters of this example, we get 0.5 for the mean of the proportional distribution and 0.2234 for the standard deviation. If necessary, review the video on proportional distributions. Now that we have the mean and standard deviation of the proportional distribution, we can approximate it with a normal distribution. If necessary, review the video on approximating the proportional distribution with a normal distribution. We can show graphically that as the number of trials increases, the approximation becomes more accurate. Let's suppose we asked 40 people a survey question. Will you vote for candidate X? There are two possible responses to this question, yes or no. Each time a person is surveyed, a binomial trial is conducted. Let's further suppose that 20 of these people said yes. This means we had a 50% success rate. That is 20 divided by 40. We will represent this ratio as P with a caret over it and call it P caret. Therefore, P caret equals 0.5. Using the equation for the standard deviation for the sample proportional distribution, we can calculate the standard deviation as 0.0791. Our interest now is to understand how accurate this sample of 40 might be. The difference between the sample proportion and the actual population proportion is either greater than a negative error or less than a positive error. If we now subtract the sample proportion from each quantity, multiply through by -1, and rearrange so the smaller quantity is on the left, we get this result. Using this inequality, we can show that the population proportion is somewhere between the sample proportion minus the error and the sample proportion plus the error. Let's now say that we want to be 90% confident that the population proportion is contained within these limits. This means that there is a 10% probability that the population proportion is outside these limits. This 10% is the value of alpha, or 1 minus the confidence interval. The 10% that is outside the confidence interval is divided into two halves, so that we have 5% or 0.05 of the area in the left tail and 5% or 0.05 of the area in the right tail. The relative standing of the boundary on the left we will call negative z of alpha over 2. It is the relative standing that has 0.05 of the area to its left. The alpha over 2 subscript just reminds us that this is the z that has half the value of alpha to its left. Correspondingly, the positive z of alpha over 2 would have an area of 0.05 to its right. We can say with this inequality that the relative standing of the sample proportion is between the relative standing on the left and the relative standing on the right. Remember that the relative standing of the sample proportion is the difference between the sample proportion and the population proportion divided by the standard deviation of the proportional distribution. We can now substitute this value into the previous inequality and get this result. Let's now multiply through by the square root of p times q divided by n to get this result. Our next step is to subtract the sample proportion from each expression to get this result. If we now multiply through by -1, we get this result. We will now simply rearrange the expression so that the smallest quantity is on the left. It is now in the same form as the inequality we developed earlier. The corresponding parts are equal. Therefore, the error E is equal to plus or minus z of alpha over 2 times the square root of p times q divided by n. These two equations will be used in determining the confidence interval. And that interval is represented by this distance. And this distance also represents the interval that contains 90% of the area under the normal distribution. In order to find the confidence interval, we will use these equations. We will use the value of p, 0.5, the value of q, 0.5, and the value of n, 40. The only value we do not have is that of z of alpha over 2. We'll use the z-table for determining these values. Let's first go to the negative z-scores and look for a value of z that has a value of 0.05 to its left. We locate in the table a value of 0.0505 and 0.0495, but not 0.05. They are both in the same row, which indicates a value of minus 1.6 for the first digit to the right of the decimal. We will interpolate the values of 0.04 and 0.05 to get 0.045 for the second and third digits to the right of the decimal, for a value of minus 1.645 for minus z of alpha over 2. To find the positive value of z of alpha over 2, we use the positive z-score table. Remember, we are looking for a value that has an area of 0.05 to its right, which means it has an area of 0.95 to its left. This is the value we use to find z of alpha over 2. The value of 0.9495 and 0.9505 are located here and correspond to positive 1.6 for the first digit to the right of the decimal. We will again interpolate the 0.04 and the 0.05 to get 0.045 for the second and third digits to the right of the decimal, for a value of 1.645. We will store these values here as plus or minus 1.645. Now we are in a position to calculate the error. For z of alpha over 2, we have 1.645. For p caret, we have 0.5. For q caret, we have 1 minus p, or 0.5. And for n, we have 40, the sample size. This results in an error of plus or minus 0.1300, or plus or minus 13%. The next step is to use the error to calculate the actual confidence interval by using this equation. For the left limit, we have 0.5 minus 0.13 for a result of 0.37. And for the right limit, we have 0.5 plus 0.13 for a result of 0.63. As a result of our original survey, we are 90% confident that the population proportion lies between the values of 0.37 and 0.63, or 37% and 63%. Now let's observe that the error equation has the sample size in the denominator of the radical. This implies that if the sample size were to increase, the error would become smaller. We can see here that as the sample size increases, the error does in fact decrease. The confidence interval becomes smaller with the same 90% confidence. This is because as the sample size increases, the standard deviation of the sample proportion is decreasing, making the distribution narrower and taller. Note that the area in the confidence interval remains 90% of the total area of the distribution. The error has become smaller, but we are still 90% confident the interval contains the population proportion. Let's bring the sample size back to 40. And note that it would be useful to know how large a sample was required to get a specified error. Starting with the equation for the error, we could solve it for n, the sample size, and have an equation that would tell the required sample size for a specified error. Dividing both sides of this equation by plus or minus z of alpha over 2, we get this equation. Taking the reciprocal of both sides, we get this equation. Next, we square both sides of the equation to get this. Now multiplying both sides by p and q, we have an equation for the value of n. For the sake of example, let's specify an error of 0.03, or 3%. That is, E is equal to 0.03. Using the other values of the example to calculate the sample size, we get 751.6736. Let's round this up to 752. Now, when we run the value of n, the sample size, up to 752, the error becomes 0.03, or 3%. For the same confidence level, we have a smaller error. That is to say, in order to achieve an error of plus or minus 3%, we need a sample size of 752.